All right, boys and girls, welcome to our first lesson in Chapter 6, our lesson on special quadrilaterals. All right, here we go. Okay, first a couple of review of some vocabulary words, which we learned back in chapter, I think it was chapter 2, but maybe chapter 3. First of all, a polygon. A polygon is a simple closed figure made up of line segments. As we know, it's a shape, right? It's a shape with straight lines. A regular polygon, important, all sides and all angles are equal. Concave is where a polygon has an angle that's bigger than 180, so it's like it's banged in. In other words, a concave polygon might look something like this, because this angle right here is banged in. Okay, a convex polygon is a polygon with no angles greater than 180, and a diagonal, like if I have a quadrilateral, a diagonal is a segment that goes from vertex to vertex that aren't making sides, so to any non-adjacent vertex. Okay, four-sided polygons we call quadrilaterals, as you know. These are some examples of polygons right here. Okay, this is a triangle because it has three sides. This is a quadrilateral because it has four sides. This is also a quadrilateral. It has four sides. Notice that it is a concave quadrilateral because the angle K is bigger than 180. Excuse me. And this last guy right here, he is a hexagon because it has six sides. We mentioned this once before, but when we name a polygon, we start at one corner at any vertex and just go around. So this hexagon could be called LMNOPQ. It could be called NOPQLM. It could be called MLQPON, but it could not be called NPOQML because you got to go around in order once you start. All right, let's keep going. These are some figures that are not polygons. This is not a polygon because it has a side that's not straight. It has a curved side. This is not a polygon because the figure is not closed. This is not a polygon because it's not simple. We have lines that cross right here at C. Okay. This is a polygon. If we call it RSTUV, that is a polygon. It would be, in fact, a pentagon because it has five sides. However, RSTRVUT again is not a polygon because it is not simple. All right, moving right along. We already talked about this, convex and concave polygons. Here are some concave ones, or some convex ones up top, non-concave. These are some concave ones here, non-convex. They're banged in. Okay, let's look at let's talk about the number of degrees we have in all of our different polygons. We know in a triangle there are 180 degrees in a triangle, and we know that because we proved that before. We know that angles 1, 2, and 3 add up to 180. Okay, by the alternate interior angle theorem, 4 is equal to 1, 3 is equal to 5, so we replace 1 and 3 with 4 and 5, therefore angles 2, 4, and 5 in any triangle add up to 180. Okay, if we look at this quadrilateral, or any quadrilateral right here, I'm going to switch colors. If I draw one diagonal, I now have two triangles. Well, these angles add up to 180. These angles add up to 180. So I have 2 times 180, which is 360. So there's 360 degrees in a quadrilateral. In a pentagon, I can draw two diagonals, 1 and 2. You can now see that I have 1, 2, 3 triangles. So 3 times 180 is equal to 540. There are 540 degrees in a pentagon. If I take a hexagon, I can draw, go back to red, 1, 2, 3 diagonals. That gives me 1, 2, 3, 4 triangles. 4 times 180 is equal to 720. There are 720 degrees in a hexagon. So the formula for finding the number of degrees in a polygon is right here. You do n minus 2 times 180. So we're just, if I want to, again, I just did the hexagon, but if I do a hexagon, I got 1, 2, 3, 4, 5, 6 sides. So I know that my degrees is equal to n, number of sides, minus 2 times 180. So D is equal to 6 minus 2 times 180, which is 4 times 180, 720 degrees. Okay, right along, if I take this figure right here, okay, I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 sides. I have 11 sides, so to figure out how many degrees there are on that, I'm going to do D is equal to n minus 2 times 180. 11 minus 2 is 9. So I have 9 times 180. I can't do that in my head. Hold up, give me a second here. 9, 1800 minus 1620, I think. You guys can check my math. All right, 1620. Down here, I got 1, 2, 3, 4 sides. That's a quadrilateral. 4 minus 2 is 2. 2 times 180 is equal to 360. So you can see I have 360 degrees in that figure. You know, again, here are the names of all your different sided polygons. A triangle has 3 sides, a quadrilateral has 4, pentagon 5, hexagon 6, heptagon 7, heptagon, not septagon, heptagon, octagon has 8, nonagon has 9, and decagon has 10. If I want to do a 15-sided figure, we're just going to call that a 15-agon. If I have a 22-sided figure, I'm going to call that a 22-agon. Okay, let's not get fancier, but I do want you to mesmerize, okay, all the sides of 3 through 10 and the names of those shapes. Okay, let's talk about diagonal. Again, a diagonal is a segment, look at that, a segment joining 9 consecutive vertices. In a triangle, there are no diagonals because all of the vertices are consecutive. They all are next to each other. Any quadrilateral is going to have 2 diagonals. You can see them in different colors. Any pentagon is going to have 5. You can see them. They make that star shape right here. They make that star shape. Let me go over that right here with my marker. 1, 2, 3, 4, and 5. Okay. The formula for finding the number of diagonals in a shape is number of diagonals is equal to n, number of sides, times n minus 3, all divided by 2. And we will discover why in class. Number of sides in this looks like a hexagon. Let's see, 1, 2, 3, 4, 5, 6. What I'm going to do is I'm going to do diagonals is equal to n, come on baby, n times n minus 3 divided by 2. I don't know why my marker's not working. So this is equal to now, 6 times 6 minus 3, which is 3, all divided by 2. 6 times 3 is 18. 18 divided by 2 is 9. Let's look at our hexagon here are my diagonals. I have 1, 2, 3, 4, 5, 6, 7. Be careful now, we don't want to repeat the same ones. 8, and the last one right here is 9. Okay? This is a 7-sided figure over here on the right. 1, 2, 3, 4, 5, 6, 7. So what I'm going to do is I'm going to do 7. That's n times n minus 3, which is 4, divided by 2. 7 times 4 is 28, divided by 2 is 14. There are 14 diagonals in that figure. So let's just talk about now the family of quadrilaterals. We'll spend a lot more time in class on this thing, but we have grandfather quad. He had three kids: trap, parallelogram, and kite. They had trap had isosceles trap. Parallelogram had twins, rectangle and rhombus, and you can't see it in my slide, but rectangle and rhombus, they begat square. We'll talk more about that in class, I promise. So, special quads, I'm just going to run through these, make sure you have these things, and in later chapters we will actually talk more about the adefs, but this is important that you know all these words. A parallelogram is a quadrilateral with both pairs of opposite sides parallel. We will talk about that definition, and there are 4 more props. Okay? A rectangle is a quadrilateral with 4 congruent angles. You will find that it is also a parallelogram, and it has one more property of its own. A rhombus is a quadrilateral with 4 congruent sides. You will also see it is also a pair, and it has 2 more properties of its own. A square is a quadrilateral that's both a rectangle and a rhombus, so it has all the properties of parallelogram, rectangle, and rhombus. A kite is a quadrilateral with 2 disjoint pairs of consecutive sides congruent. If you want to, you can just cross that word out. It's used in every book. I'm not quite sure what disjoint means, but it means that, well, basically what we're saying here is I have 2 sides that are congruent next to each other, 2 pairs, but they're not congruent to each other. So this right here is a kite. These 2 sides right here are congruent. These 2 sides right here are congruent. Believe it or not, this is also a kite. This side is congruent to this side, and this side is congruent to this side. It is just an example of a convex kite. All right? A trapezoid is a quadrilateral with exactly 1 pair of parallel sides. An isosceles trapezoid is a trapezoid with congruent sides. So it has 1 pair of parallel sides and 1 pair of congruent sides. Okay, you guys know this. The area of a triangle is 1/2 base times height. The area of a rectangle is length times width, or if you prefer, base times height, where this being the base and this being the height. Okay? These 2 sides, the height and the base, the length and the width, or the base and the height, they must always be perp. Whenever you find the area, you got to multiply perpendicular sides. Okay? So the polygon exterior angle sum. This is a very hard formula to remember. Please remember it. Whenever we talk about exterior angle, so here's an exterior angle, here's an exterior angle, here's an exterior angle. These are all exterior angles. When I talk about the measures of an exterior angles of any polygon, no matter how many sides it has, you take all those angles, and every single time they are going to add up to 360. So in other words, if I'm going to write that formula out for you, the sum of exterior angles is equal to 360. Done. Okay, so let's do a couple of problems here. Let's first find the sum of the measures of the interior angles of a convex heptagon. Heptagon means 7 sides, so I know that the degrees, helps get my pen out, here we go. The degrees, D, is equal to n minus 2 times 180. Well, n is 7, so this is going to be 5 times 180, which is 900. 900 degrees in the sum of the interior angles of a convex 7-sided figure, also called a heptagon. Find the measures of each interior angle of the quadrilateral. Well, I know that the sum of the measures of all those angles is equal to 360. So I know that x plus 3x plus 90, because I have a right angle, plus 90 is equal to 360. I'm going to add up my x's. 4x plus 180 is equal to 360. minus 180 from both sides. 4x is equal to 180. Divide by 4, x is equal to 45. So this angle would be 45, and this guy up here is 3 times 45, which is 135. Let's do one more here. The poles of a tent, when properly positioned, they form a regular hexagon. What is the measure of the angle formed at the corner of the tent? So I'm going to have a hexagon. That's 6 sides. The fact that it's a regular hexagon means that all sides and angles are equal, just like in my picture. So if I know that the degrees of the total of this, I know again, I'm going to use the formula 180 times n minus 2, n is 6. So I have 180 times 6 minus 2 is 4, or 720 degrees. I'm now going to take that number and divide by 6, because I'm going to have 6 angles if I have 6 sides. So therefore, 720 divided by 6 is 120 degrees. There's 120 degrees in each of those corner angles. All right, guys, we got one last problem here. We're going to use a formula that we're going to add to the formula that we know for the number of sides that we used in the last problem. We know that the total measure of the interior of a polygon, the total measure of the interior angles is D is equal to 180 times n minus 2. Well, if I want to find each angle, all I do is, of a regular polygon, I just take that total number and divide by the number of sides. So that's n. I'm going to divide by n, so D is equal to that. So what I'm going to do right now, I'm going to do this problem. I know that the measure of the interior angles of a regular polygon is 135. So that's 135 is equal to 180 times n minus 2. We're solving for n, all over n. I'm going to now multiply both sides by n. So I have 135n is equal to 180n minus 360. I'm going to actually subtract 180n from both sides. So I get negative, I'm doing the math in my head here, negative 45n is equal to negative 360. Divide both sides by negative 45. And n is equal to 8. So the name of this figure was an octagon. All right, folks, have a great day. We'll see you soon.